So we're going to be in section 5.3. And so 5.3 is linear inequality systems, which is what we have been doing, where we were graphing lines with shading. But we're going to look at some applications of this. So we're going to look at some solutions involving profit and cost, since this is a business math class. And you will have possibly some classes that go into a lot more of this. We're just really kind of introducing a lot of topics this semester that as you move forward with your business degree, you might cover in more detail. So I think it's kind of obvious, but let's make sure we say this. We typically want to minimize cost and maximize profit. So often people focus on increasing profit by increasing sales, and that is a way to increase profit, but you also can minimize your costs, and then you pocket more money that way. And it doesn't always involve, having to sell more items. So based on the types of graphs we've been looking at, there is a concept called the method of corners. And all the method of corners says is that the max or min must occur at a vertex or corner of a shaded area. So the handout that I gave you, I don't remember which one was on top. Let me look. So if you want to, the handout that I gave you today, you can kind of leave room for it and you can cut it out, kind of like I'm about to show. So I've already kind of cut a piece, but I want us to look at this graph. And I wasn't confident that you would be able to see the details in this weirdly shaded room or lighted room. So it's the first graph that's on your page, and again, if you just want to leave a blank and you want to cut it out and paste it later, you can. Okay. So we have this graph, right? This is a graph similar to the one that you showed me for your quiz today, right? Your warm-up. So notice we have this shaded area, right? Is this a bounded graph or an unbounded graph? This is a bounded graph, right? It's completely bound on all sides. And so what if I asked you to use this graph to find the max, and let's say that I'm going to give you two parts. The first one, I want you to use the following profit equation, 4x plus y, and then I'd like you to skip a little space. We're also going to look at a second profit, which looks like 9x plus 3y. But it's all going to be subject to this graph here. And again, I know the lighting's kind of crappy, so you can look at your own handout. So essentially, we are going to realize that the max can only occur at what kind of values here. We don't need to worry about anything in the middle of the shading. We only need to worry about the what? The corners, right? So a max has to occur for any equation at one of those four corners, right? So you don't have to do it this way, but I'm just going to organize it in kind of a table. So we've got some different corner points, right? What are the corner points if you look at your graph? 0, 0, 10, 0, 7, 9, and 0, 12. And the equation that we'd like to maximize is this profit of 4x plus y. So we are literally going to find the values of profit for each of the X and Y combinations. Okay, so no profit here, or right, no surprise here probably. If you have 0 and 0, you're going to profit 0. For this one, if you plug in 10 plus 0, you're going to get 40. For this one, plug in 7 for X and 9 for Y. You're going to get 28 plus 9, which is 37. And then last but not least, 4 times 0 plus 12 is 12. Okay, so where's clearly the max then? Right here, right? This is the highest value. So the answer then would be, for this one, I'm going to slide this over. For part A, the max would be the point 10, 0. So if this represented like 2 different items we were selling, so let's say it was like hamburgers and hot dogs. We had a concession stand of some sort. So it's telling us that to make the maximum profit, we should sell all of one item and none of the other. Okay, so if X was hamburgers and Y was hot dogs, it would be sell all hot dogs, sell all hamburgers, no hot dogs. Okay. All right, so let's look at part B. Notice that the points are not going to change, but the profit equation does change. So I'm still going to compare only the corners. That's what the method of corners tells us. We don't need to pay any mind to the points on the inside because those are never going to be the max. So again, let's plug it in. So P equals 9 times 0 plus 3 times 0 or 0. P equals 9 times 10 plus 3 times 0, which is 90. P equals 9 times 7 plus 3 times 9. So that's going to be 63 plus 27, which is 90. And then lastly, P equals 9 times 0 plus 3 times 12. So it looks like 36. So this may not happen too often, but the values are both maxes, right? So the max is 90 at the point either 10, 0 or 7, 9. So back up here, let's write it a little differently so that I kind of use the same formation here. So the max was 40 at the point 10, 0, because that's a little more descriptive anyway. So what this means is we could sell 10 of one item and 0 of the other item, or we could sell 7 of one item and 9 of the other. Okay, so notice this is often what a profit graph is going to look like because it doesn't go on forever and ever and ever. Okay, profit usually has a peak, and we want to strive for that maximum profit. Okay, so I don't think I'm going to have room to squeeze it in, so I'm going to look at the next graph now. So the next graph on your handout should look like this. So I want you to use the graph to find the min. By the way, notice this is not a bounded graph, so I know the lighting sucks in here. But if you look at your picture, I'm going to try to see if I can get it at least in a better spot. Notice that it does stop here, but do you notice that it just stops there because the graph happens to stop there? Like it would continue out further. So this is actually an unbounded graph, not a bounded one, right? Because actually costs can continue to grow forever and ever and ever, right? The more items you make, the bigger cost will be, and there's not really a peak for costs if you keep making more items, you're going to continue to incur more costs. So let's take a look at that graph. And we're going to find the min for the following cost functions. So let's say cost equals 7x plus 4y. And again, skip yourself some space. Let's say cost equals 2x plus 11y. So we'll do it much the same way. It can only be a corner point. It's going to be the point 4, 3, 15, 0, 15, 15, and 0, 15. So let's plug it in, but this time we're not looking for the highest one. We're looking for what? The lowest. So 7 times 4 plus 4 times 3, that's going to be 28 plus 12, or 40. This one, it's going to be 7 times 15 plus 4 times 0, which is 105, I think. 15 and 15 would be 7 times 15 plus 4 times 15. So that's going to be the 105 plus 60, so 165. And then lastly, 7 times 0 plus 4 times 15 is 60. So where is the minimum cost found then? Yeah, so the minimum is 40 at 4, 3. So if we were talking about production of some sort, that means you should sell 4 of one item and 3 of the other, and you will have the least cost you can possibly have. I forgot to write this equation here, so I'm going to do that now. All right, so let's look at part B. So again, the method of corners tells us that the max and the min can only lie at a corner. So that was why on your quiz today I asked you to be really, really careful about where they crossed each other, because the corner pieces / the intersection points are going to become super important because they're the only place an answer can exist. So this one would look like, oh, that's not the right equation, right? I switched it to 2x plus 11y. So this is going to be 2 times 4 plus 11 times 3. So 8 plus 33 is 41. This one's going to be 2 times 15 plus 11 times 3, or 0, I mean. So it's going to be 30. This one's going to be 2 times 15 plus 11 times 15. So that's going to be 30 plus, I think, 165. So, yep, it's going to be 195. By the way, it shouldn't surprise us that this is coming up with the biggest cost, because this is making the most number of things, right? If we were talking about 2 different kinds of items, we're making 15 of one item and 15 of the other. So, of course, we're going to have the biggest cost there. That's really not a shocker. And so 2 times 0 plus 11 times 15 would be 165. So, of course, the min up here was the 40, right? And the min here is the 30. Okay. So the min is 30 at the point 15, 0. So if your goal was to minimize the cost, you should make 15 of the first item and none of the second item. Okay. So there will definitely be some problems where you have to come up with the graphs yourself. Okay, so that can be kind of the challenge. So if you had your graph paper from last time, trying to think see if I brought any. I did bring some, so if you needed to come get some, I'll put them up here. So basically what I'm going to do is combine what we did last class with what we're doing today, whereas you have to come up with your own graphs, and then you have to come up with where the corner pieces lie. So let's start one of those. So let's say that I asked you to maximize the profit function of 3x plus 2y. Now when I say maximize, what does that mean? Find the what? Find the maximum, okay? And let's say here are the restrictions. X plus y can't be bigger than or equal to 6. X has to be less than or equal to 3. And x and y are both bigger than or equal to 0. So the first thing I need to do is to be able to actually graph these things, okay? And so we're going to do the shading thing, okay? I'm going to get my Post-it note to fit here. So what's the only equation I actually need to probably do any work on? Yeah, the first one, right? So x plus y is less than or equal to 6. Remember, we need to make these solve for y, right? We need to make these look like y on one side. So it's going to be y is less than or equal to negative x plus 6. So from last time, what does that mean? That means I have a y-intercept of what? Of 6, and I'm going to go down what? Down 1 over 1, right? So it's going to have a negative slope, kind of like this. So it's going to look like this when I graph it. Okay. I do need to pick a test point, but I'm going to kind of fudge and quicken this up a little bit, right? If I want less than, which side am I going to be shading? So you can just pick a test point mentally, right? Let's pick 0, 0, right? So is 0 plus 0 less than 6? It is, right? Which means I need to shade under, right? So I need to shade below. So remember I gave you this trick. You can just kind of do this that says, hey, I want to shade under, rather than have to worry about all your overlapping shading. Let's go on to the next statement. What did we say about x? X had to stay what? Less than 3. So here's x equals 3, and we want to stay less than that, which means we want to be on this side, right? And then x and y have to both be positive. So we're basically talking about this little strip right here. Okay, so what am I really trying to find here, though? Okay, yeah, I'm just supposed to find the corners, right? I want to know what the corners are because those are going to be the only places where my max could lie. And so that's why I need a pretty decent graph to be able to find the corners. So let's go ahead and list the corners out here. And our profit equation we want to maximize is 3x plus 2y. So 0, 0 is the easiest corner point. Okay, and then just kind of go around, right? What's this point? What's the point that's right here? 3, 0. What's the point that's up here? If you graphed it well, it should look like 3, 3. And then what's the point at the very top? It's the y-intercept, so that should be easy to pick out. What's the y-intercept? 0, 6. So what am I going to do? I'm going to plug these in, and I'm trying to find the which one, biggest or smallest? The biggest, right? So this one's going to be profit of 3 times 0 or just 0. This one's not really that interesting. And by the way, 0, 0 better not be your maximum profit, or you probably don't need to be in business, right? It means you should not sell anything, and that would be your maximum profit. So that would be a big business fail. 3 times 3 is 9. So that's what you get for that profit. 3 times 3 plus 2 times 3 is 9 plus 6 or 15. And then finally, 3 times 0 plus 2 times 6 is 12. So the max is what? Yeah, the max, that's not the biggest one though. What's the biggest one? Yeah, the max profit is 15 when... Right here, right? The biggest one, this one's 12. So when x is 3 and y is 3. Let me slide it up. Okay, so we're going to look at some more of these, but If you're wondering kind of what these represent, we're going to look at some word problems probably the very next class. We probably won't have time to get to it today. But what these represent is it's not always feasible for us to just make as many products as we can. We probably have limitations on what kind of products we have, right? For instance, in my hamburger and hot dog example, you don't just have probably an unlimited amount of hamburgers and hot dogs, right? You have a limited portion that you have to sell, okay? If you are making or manufacturing something, you don't have an unlimited amount of workforce and you don't have an unlimited amount of supply. So very, very often you will have some boundaries. Now these are really tiny numbers, but you will have some limitations. Like I only have, you know, so many hours that I can make my employees work to make these items, right? Or I only have so-and-so number of machines to make this product. So it's not just a, you know, make a gabillion items. You have to actually make sure that's practical, okay? And so that's where linear programming comes in, and that's what this is. This is linear programming, like what are my limitations, and then how can I work within those limitations to maximize or minimize the quantity that I want to. Okay, so let's look at one more maximizing profit, and then we'll look at a minimize question. So let's say that I want you to maximize the following profit equation, but you're subject to these restrictions. 2x plus y has to stay under or equal to 6. X plus y must be less than or equal to 4. X must be less than or equal to 1. And x and y both have to be positive. If we're talking about profit, you know, x and y are always going to have to be positive, right? Because we can't sell or make a negative number of anything. So to kind of save some time, I'm going to show you what the two equations look like, and we're going to kind of graph them as we go. So the first one would change into negative 2x plus 6 if you solve for y. So let's graph that one. Trying to make it straight here, but all right, so what is this going to be? Y-intercept at what? 6. And I'm going to go down to over 1. So it's going to look like this. So my graph is going to have to be pretty tiny. This is where a larger grid graph paper kind of comes in handy. If I want, and I'm going to call this equation 1, just so that I don't get confused with the second equation I'm going to graph, which I'll use a different color for, but it's nice to label it there. So which side am I going to be shading? I'm going to be shading, I'm going to go down here, but I'm going to shade this side. I'm going down at the bottom because I don't want to muddy up the top where I'm going to be shading. Okay. So let's look at equation 2. Equation 2, if you solve for y, is going to look like y is less than or equal to negative x plus 4. So this one is going to have a y-intercept of, and actually I drew that one wrong, didn't I? So that's what's good about this. Right, I didn't cross it at 6, I crossed it at 4. So let me start over there. All right, so back to the first one. I should have went up this high, I just didn't. Which is going to mess with my points, so it does need to be correct. So we're still shading on this side, but it needed to look better than the way that I had it. Okay, so that's equation 1. I just had it crossing at the wrong spot. Equation 2 is going to cross at 4, right? The y-intercept is 4, and we're going to go down 1 over 1. Notice if you keep going down 1 over 1, you're crossing right here, okay? So this is an important point. This point right here, it's the point of intersection. So that is going to be significant for us because it helps describe one of the corners. So here is the second equation. And again, if you're going less than, we're going to be shading on this side. So what other restrictions as you look down the list are there? Y has to stay what? has to stay positive and less than 1, right? So for mine, it's just going to be this little tiny sliver here if I use every box as a unit. So it's going to be just this little strip here. But your graph paper you have should be a little wider grid. But it's a pretty small little area, right? Okay. And of course, which points do I need to find / pay attention to? The corners. So let's list the points here. So the point 0, 0, the point 1, 0. What was their intersection point? It ended up not really mattering, right? Because I didn't end up going out that far anyway. Okay. So what's actually this point right here? And again, you might want to look at your own paper. But that's over 1 up 3. And then 0, 4 is this top point right here. So it's really, really important that you graph this on your own graph paper because mine, frankly, looks a little small. And so yours is going to be a lot more meaningful when it's right in front of you. But let's plug in these corner pieces. So 0 plus 3 times 0, no shocker, 0. This one is 1 plus 3 times 0 or 1. This one is 1 plus 3 times 3 or 10. And then this one is 0 plus 3 times 4 or 12. So which one is our biggest one? This time 12 is our biggest one. Okay. And notice that we find it by basically selling all of one item and none of the other. So the max profit is 12 when X is 0 and Y is 4. Okay, so let's do one where we're minimizing, but really I don't think it's much different. We're just going to do the same things. We're going to graph, but then we're going to find the smallest one. So let's say that this is my cost function. So by the way, this means if we're selling 2 different items, the first one costs us $2 each, the second one costs us $5 each. So let's say that here are my restrictions. X plus Y is at least 3. X plus 2Y is at least 4. And X and Y still have to be positive. Whether it's profit or cost, the X and Y are going to have to be positive.
Is minimum always going to be cost and maximum always going to be profit or not?
Yeah, you always want to maximize profit and minimize cost. So
I just like something.
yeah. Okay. So yes, to answer your question, that is true. All right. So let's come up with some graphs for these. And note, just like throwing up a graph is not going to be good enough for these. You really need to be pretty detailed. So this one's going to look like negative x plus 3 if you move the x over the first equation. So that means it crosses the y-axis at 3. I'm going to use, for my graph paper, I'm going to start using the slash marks for the ones just because I need more space. So I'm going to go down 1 and over 1 like this. Your graph paper you have should be a little bit wider. I'm just having trouble squeezing my graphs in on these. But this time we want to go greater than, right? Which if we pick our test point, which side do you think that's going to end us up on? It's going to end us up this way, okay? So we're going to shade this way, and I'm going to call that graph number 1. Okay, equation number 2, again, you would solve for y. So tell me verbally what you would do here to solve for y, where I'm pointing. First, you would subtract what from both sides? The x, and then you would divide everything by 2. Okay, and if you do that, you should get y is greater than negative 1/2 x plus 2. So that means the y-intercept is up at 2, and I'm going down 1 and then to the left 2, down 1 and then to the left 2. So this is a shallower slope. So we end up getting this line. So this is equation number 2. And again, we want to only shade the things on this side of the line. So if we want to know where they intersect, it's actually here. This is a what kind of graph? This is an unbounded graph. But we do need to stop at the axes, right, or the axes. All right, so notice there wasn't any kind of stopping point on the top side. It's completely unbounded on the top, okay? So when you go to find the corners, you might notice that we don't have really a top right corner, right? We don't really have that, right? So we actually are only going to have how many corners on this one, since we don't technically have the other? You're only really going to have 3 points, right? But our cost equation is 2x plus 5y. So sometimes you'll have a point up here where it says, hey, stop here, and sometimes you won't, okay? But we just need to figure out what all of these points are. And so you're going to have to maybe pay particular attention to kind of where it crosses, right? So first of all, I'm going to start with over here, okay? Over here, it's the point 40. And again, that might be easier to see on your graph, okay? But it's actually all the way in this corner over here. It's right here. Okay, so that's the point. Where I'm pointing my pen right now is the point 40 because I went 2 every time, if you remember right. Okay, so 40, where's this point? 2, 1. And then the point up here in this corner is 0, 3. So I get C equals 2 times 4 plus 5 times 0 here, or 8. Here I get 2 times 2 plus 5 times 1, or 9. And here I get 2 times 0 plus 5 times 3, or 15. So we're looking for the smallest one, so it's this one. So the minimum cost is 8 when x is 4 and y is 0. Sorry about that. Let me slide that up. Okay, so I'm going to write this just for my own benefit, but note the scale factors too on this, on my graph. You don't have to write this on your graph. So I just decided to leave myself a little bit more space. Okay. So kind of where we're heading with this, where we're going to begin in the next class, is we're going to be graphing some real life scenarios that might have kind of larger numbers. And so before we close for today, I want to go over some alternate ways to graph lines. Okay, because we've been graphing lines in one specific way, and we might need to transition away from that with some of the other bigger number graphs. So the first way is to plot the y-intercept and then count the slope from there. That's how we have been doing it. But a second way is to find the X and Y intercepts, and connect them. So if you remember right, I know it's been quite a minute, but this is how I had you graph on the competency exam, if you remember. You had to find the X and Y intercepts, and then you had to graph a line. Just because it's been a little bit, do you remember how to find each of the intercepts? So how do you find the x-intercept always? Set y to 0. And then, of course, how do you find the y-intercept? Set x to 0. So the biggest issue with these graphs that are going to have larger numbers is we also are going to want to know where the intersection points of multiple lines are. So to find the intersection points of a linear system, we already did this all the way back in Unit 1. It's just been a minute. Okay, so I'm going to remind you of the two methods that we really used. The first one was matrices. This was on test 1. Remember, matrices solve system of linear equations. Okay, and then the second one that we talked about before we talked about matrices was the addition/elimination method. So moving forward to next class, we're going to focus on graphing with X and Y intercepts. So notice I put a star by that one. And we're going to focus on finding intersection points using the addition and elimination method because I think it'll be a little bit quicker. Okay, so there's always more than one way to do something. Okay, so we're going to transition away from necessarily counting the slope and the y-intercept. Okay, because just to give you a preview of kind of where we're heading, I don't want you to write this down, but this is the type of equation that we're going to look at next week. Notice the numbers are quite larger, and these values are super big. Okay, so what would be the problem with trying to graph these lines with the traditional method? The y-intercept is going to be pretty big, right? And the slope is going to be pretty big. So your graph paper is going to have to be a little unreasonable. Whereas finding the x and the y-intercept of these is kind of easy peasy, right? It's not really that big of a deal to find the x and the y-intercept. So that's why we're going to kind of transition away from the way that we have been graphing lines, which works perfectly fine when the numbers are small and manageable, but not so good when the numbers are large. Okay. So moving forward, next class, just make sure that you bring a calculator. You won't even really need your graph paper, but you can always grab some more graph paper on the way out if you feel like you're going to need it for your homework. Okay. So when is your